Yeah, good morning. So privacy techniques for data science in regulated environments. Don't worry, I'm not just gonna go over HIPAA and GDPR and make your eyes bleed on all the regulations you have to deal with, because I don't like it either. We're gonna do some math to see how we can deal with all that stuff. So, let's see here. I am not clicking. Here we go, me. All right, so yeah, I started, as he said, doing data processing. I worked on a lot of radar systems. Radars produce a lot of data and need a lot of math to figure them out. So after doing that for a while, I found another place that has very interesting problems and a lot of data. It was the National Security Agency. So there, they have a lot of data, a lot of computers, and it is a highly regulated environment. A lot of people think that we just have free access to everyone's everything, but that's actually not the case. They actually control it very well. And I was part of the group. Oh yeah, here, kind of got, it's a lot more complex than this. Select star where hobbies equals terrorism group by country. Yeah, if it was that easy, if everyone could just register for that database, that'd be great. But they don't. So we created Apache Accumulo. It's a Hadoop-based distributed database, much like HBase. What's different about it, though, is it has privacy controls built into the database. So every piece of data in that database has access control restrictions applied to it. So they have this concept of having all the data in one giant database, but no one has access to all the data. Every search and every scan of the database is well regulated, and you only get to see what you're allowed to see, based on either what you're doing or your clearance levels or whatever. So that gets people a little nervous. So you have this database and you don't have access to all of it. Like data scientists want more data. That's like your main goal, right? Just find more data and we'll throw it at algorithms and we'll figure stuff out. But the truth is, like, you never have all the data, right? Like the world is the only place that has all the data. Any data you have is just a sample of the data. So get used to having less data, even in this world of big data, because that's how you never have all the data. And just kind of realizing that and dealing with that will make your data science life go easier, I think. So after the NSA and Accumulo and my select star, a group of us left and formed a company called Immuta. And Immuta is really focused on taking the lessons we learned kind of at the intelligence community and their problems of regulating data and data access controls, and we realized the rest of the world kind of isn't doing a whole lot of that, but they have a lot of regulations coming down the pike. So we built Immuta. I'm not going to kill you with a big sales pitch, but we have a table out there, and we kind of provide a centralized place to do data governance and access and control your data. Kind of more interestingly, a lot of the techniques that I'm going to be discussing here in a minute, we're baking into Immuta, so you'll start to get some of these privacy techniques kind of for free. Well, it's not free, but you get the point. So yeah, why do we care? We have things like the EU GDPR coming down the pike. People heard about this? I assume most people in this room would have. And you might say, why do I care? I'm in the US, what's that have to do with me? The problem is it applies to all the EU citizen data. So they kind of view data about a person as an extension of that person, and that person has rights to the data about them. And to show they're serious, the law has penalty of up to 4% of your global revenue for violating someone's privacy, right? So if you're Apple and you made, your global revenue was about, what, $216 billion last year, and you get nailed with a fine of upwards of $8 billion, that's that's a problem. Like that's going to affect your stock price more than going onto a plane and beating up your customers, right? So, and to prove they're serious, this is actually like a screen cap of the GDPR main website. And you'll notice they have like a doomsday countdown clock going on their website that this is going to be enforced. Like, so they've passed the law and they said, we're going to start enforcing it. So like on that, when that goes to zero, I assume there's going to be an explosion of lawsuits. So what are we going to do about this? You know, these lawyers are regulating data privacy. So yeah, first thing we do, we just kill all the lawyers. But that's not really practical, and I find data scientists aren't really aggressive people. So let's use statistics, something we're much better at. All right, so in this talk, I'm going to talk about different ways of dealing with data privately. So people want to release data and share data. This is the Open Data Science Conference. But we need to make sure we do it in a private way that protects people's privacy and protects your company's bottom line, whichever one you're more interested in. So we can collect data in a private way, we can release data in a private way, and we even have ways of privately interacting and doing data science analysis with data. So yeah, kind of my goal is to retrain your data science brains. We have all these great algorithms out there that you've been learning about, but let's bake privacy into those algorithms and kind of get the best of both worlds. So the first technique is kind of the one that probably comes to everyone's mind when they first think about privacy. It's k-anonymization. So you want to produce a release of data with scientific guarantees that individuals in the data cannot be re-identified. Great. And the important part is that the data remains useful, right? We want the data to remain useful. So k-anonymization, people think of masking, kind of rolling up and generalizing some fields in the data. This is an example of a k-anonymized table from the initial k-anonymization paper. And you'll see here you have 4 columns that are demographics and a sensitive column, this problem column. So what you're trying to do is hide the fact that these people have, that individuals have certain problems. And so if you look at T7 and T8, they have the same demographics, but different problems. So if you search, no matter how you search based on demographic, you're always going to get 2 results back. So you'll never know who that is. So that's k-anonymization in a nutshell, but interestingly enough, in this initial paper, they kind of showed a flaw of k-anonymization, which is this bottom row, where you have the same demographics and multiple, and you know, 2 problems, but the problems are the same. So those individuals are not really protected because you have the same problem. So if you happen to be, you know, a white male born in '67 living in that zip code, you have chest pain problems if I know you participated in this. Even though you're not the person with those particular, you know, even though there's more than one person with those problems. So k-anonymization becomes increasingly difficult to calculate on real data. You need to roll up and generalize your data to maintain k. Then there's also this question is what is k? Like you need k of 2 to start with, but once you've calculated k and accounted for k, is your data changing in the background? You know, your database is getting updated. How do you maintain this k privacy number? So to combat that, researchers started coming up with different ideas. One is L diversity. And that's ensuring that that's combating that problem of those last 2 rows. So it's ensuring there's ample diversity in your groupings of k. So not only do you have to form these groupings, you have to make sure that there's ample diversity within those groups of the problems you're trying to hide. So then another problem with it is people started to look at those k groups and perform statistical analysis against them. And they found that really those groups should have proper statistical distribution of the overall data set of those issues. or else we'll be able to exploit that your K groupings have different statistics than the overall statistics, and we'll be able to narrow in on people. So that's even harder. Great, now I have to learn the statistics of all my data while I'm trying to figure out all my statistics of my data and group everything and expose it. So kind of in summary, there's many attack vectors available to de-identify K-anonymized release data. There's linkage attacks, temporal attacks, and complementary release attacks. There's all kinds of papers out there on it and kind of how K-anonymization isn't the best thing to do. There's also been very public cases where companies tried to release data that has been, quote, anonymized, and researchers took that data and de-anonymized it. So if you're worried about your bottom line at your company, like AOL had this search term data dump. It was great. It was 3 months of searches, 20 million terms, 650,000 users. And it was great. Data scientists love it. They love big data dumps, and you get to learn stuff. However, what happened was researchers got a hold of it, and they identified AOL person 4417749, Miss Thelma Arnold, who was a 62-year-old widow in Georgia with numb fingers and a dog that urinates on everything. And you'll see her picture, like her dog's even wearing a diaper there. Like, we know way too much information about Thelma Arnold now. And so this was actually a big problem. The CTO of AOL was fired pretty instantly. CNN Money came out with a segment titled 101 Dumbest Moments in Business and ranked this number 57. It was a big problem for AOL. And you guys can probably know that you don't really go to AOL to do searches anymore, right? So yeah, it's a problem trying to release data. Another one was this Netflix prize. They had this $1 million prize, improve their movie recommendation system. And what happened was, get rid of my notifications here, was that researchers went to IMDb and they said, hey, movie nerds are movie nerds. They're gonna start ranking movies all over the place. And turns out people that watch movies like to rate the same movies all over the place, and they give them very similar ratings. So researchers correlated the Netflix data that they released to do this competition with IMDb, and they were able to identify several individuals in the data based on their IMDb profiles. And the Federal Trade Commission got involved and actually sued Netflix, and Netflix canceled any further competitions to try and have data science improve the recommendation systems. So finally, here's a New York City Taxi and Limousine Commission was a result of a FOIA request for taxi data. And yeah, they just went to the taxi commission and said, hey, can I have this data? And they said, yeah, bring a hard drive by, we'll dump it for you. And they did like an MD5 hash on some of the fields in the taxi data and said, oh, that's probably anonymized. Boom. Turns out taxi numbers, how they identify them, are not really very random strings, and you can just create a rainbow table and attack that and de-identify things. So there's an article out there written where they identified celebrities by correlating paparazzi pictures with time-stamped photos with cab numbers on them, looking up their trips and finding out, Judd Apatow took a trip and paid this much money and tipped. And there's another one, Bradley Cooper went from Tribeca to Bank Street, $9 cash, and he didn't tip. What a shame, Bradley Cooper. So, I'm sure he's thoroughly embarrassed. But yeah, even good intentions can have problems with just trying to K-anonymize data. Immuta, our CTO, Steve Tao, sitting right over here, did a blog post on KD Nuggets you guys can go look up, where we took this taxi data and we did a more anonymization on it, where this is just a brief way to show this is the original data, and it has this very precise location data in it, and we're able to kind of randomize the locations a little bit. And you can see that even though at a low level the locations are kind of regularized, but your global statistics really remain the same. And that's kind of the point of, you can do anonymization in many different ways and kind of still be able to do interesting stuff with your data. So yeah, in all these cases, what could have been done differently? They just anonymized the data and released it. Turns out that's a bad idea. So we can look at other techniques to help with data privacy. So how about changing the way we collect data initially? If we could collect data in a private way, we could do what we want with it because it's already been privatized. So like, for example, in the latest election, you'll notice the pollsters didn't really get everything right. Like, why was that? And it was a particularly tense election, and people didn't really want to admit that they voted for Donald Trump, but obviously some of them did. But you know, they might not have wanted to admit it, or they didn't trust the system, thought they were being logged by the man or something. So maybe they lied or whatever, but the pollsters didn't get it right? So what could have happened differently? So an answer to that is a technique called randomized response. Now, randomized response is a way to collect sensitive data privately. So if you have a question in a public forum like this that people might not want to just raise their hand and admit that this is the case, excuse me. This technique is a way to collect that data and preserve people's privacy and kind of use statistics to get the information you want anyway. So I'm going to ask you all a sensitive question, and don't all raise your hands at once. We're going to raise our hands in a minute. But so the question is, who here has a secret Tinder account that their spouse might not know about or whatever? So that's a sensitive question, right? You don't want to just like raise your hand, but like I'm a researcher. I need to know this information to figure out the psyche of data scientists at ODSC. So how do I get that info without everyone just blindly telling me and me judging you? So what we do we rely on plausible deniability. So everyone, we're going to roll an imaginary die here. So everyone think of a number between 1 and 6. Get that in your head. Now, what I want you to do is everyone that thought of the number 3, you're going to raise your hand, and raise your hand if you have a secret Tinder account. So, all right, everyone that thought of 3, raise your hands. And if you have a secret Tinder account, raise your hands. Only 2 people? Come on, no one thought of 3? 1 to 6, come on, that's statistically impossible. You guys just aren't thinking. You're ruining this whole thing. My question was way too sensitive, apparently. So now I know you all have secret Tinder accounts. But what should have happened here is, like 1/6 of you should have raised your hands, and the people that have Tinder accounts should have filled in with that noise, right? So you're protected by this group theory. Like, people just have their hands up, and you also have your hands up, but no one really knows why your hand is up. It could have been a random me telling you to raise your hand, or it could have been a yes to this question. So, fortunately we have math, right? And we can back that out. So back at our booth, we can actually go through this in excruciating detail if you want, but we can calculate the true proportion given the proportion that is just telling you yes blindly, given enough samples. Not the 2 people that raised their hand probably would blow this out of the water. But yeah, so you can use math, and you're adding noise before you collect the data. So you don't really know for sure what everyone's answer is, and that's kind of protecting their privacy as you're collecting the data. And companies are using this technique. So Google Chrome and Apple announced they're doing something similar. When you send anonymous usage statistics back to Chrome, what they're actually doing is they released a paper called Rapport, Randomized, Aggregatable, Privacy-Preserving Ordinal Response. So it's clear what they're doing, but no. What they do is they take your settings in your browser, and they apply it to this giant Bloom filter of settings. They kind of hash each setting and find a bit to set, but they add random noise to those Bloom filters. So, in the browser before they send them back to Google. So Google gets these bit vectors that have, bits set for the true settings, but they also have random noise in those bit vectors. So they never know what your true settings are because they just have bits, and some of those bits are your settings, and some of those bits are set, but they're not actually what you have set. So what they're able to do, because they're Google and they have Chrome, they have a lot of users, they're able to take those bit vectors and beat them against each other and beat out this random response, that random noise, and get at the true proportion of people that have their settings a certain way and correlate that with crash reports and preserve your privacy so they don't know that you browse in incognito mode all the time or whatever. They don't really know that, but they can find out that incognito mode is causing data crashes in general, and that's really what they care about. They kind of don't care what your particular settings are. So, oh yeah, the paper is interesting too. It's not just this little formula that they use. If you read that paper, they don't really divulge how they beat these Bloom filters against each other, other than it's, quote, advanced statistical techniques. I guess it's probably a lot of averaging and stuff, but I don't know. I don't have enough Bloom filters to try and figure it out on my own, but maybe someday they'll tell us what these advanced statistical techniques are. So on to data interaction, and maybe this is more relevant to what people are after here. There's this concept called differential privacy. So it formalizes the idea that a private computation should not reveal whether any one person participated in the input or not, much less what their data was. So kind of contrary to k-anonymization, it's protecting whether you even answered the survey or not, much less what your answer would have been, may or may not have been. So this is a quote from Frank McSherry. He's one of the original authors of the differential privacy paper. And I recommend his blog. Very opinionated and interesting on differential privacy. So what is it? It's nice. Rather than k-anonymization and other techniques, it provides mathematical guarantees of anonymization. And how it does this is you have two data sets, D1 and D2 here, and you want to find some statistics out about those data sets. And those data sets differ by one entry, and that's the entry you're trying to protect. It could be any particular entry. Maybe it's your data, maybe it's not. So what you want to do is you want to run some aggregate query collecting statistics over this data. We'll call that M, or fancy M, because we're all proper mathematicians and that's how we write M's. The definition of differential privacy is that the probability that, the probability that your query over data set 1 differs no more than the same query over data set 2, by some e to the epsilon factor. So it guarantees that, the same query over two different data sets is not going to vary more than that e to the epsilon. So that's interesting, I guess. It doesn't really tell you how to do it. But this is the mathematical guarantee that you have to prove that your technique complies with for a differentially private system. So to implement this, let's talk about sensitivity and robust statistics. So sensitivity of a query is defined as the maximum difference of any output of your query of any two data sets that differ by one entry. So if your data items are kind of the set of real numbers, then the difference in any query over the set of real numbers with one real number being different is kind of infinite, right? So that's a problem. So you might have to bound your data, know the practical bounds of the columns of your data so that you know you can properly calculate the sensitivity of queries over your data. So as an example here of sensitivity, it's the typical housing situation where you have houses that are all generally around the same price, but you have this $30 million house at the end of the block, and you're trying to calculate statistics of houses, but you want to protect the privacy of each individual house. So if you look at the sensitivity of various queries on that simple data set, and if you look at the mean of that is going to be about $30 million, right? So if this is data set 1 and data set 2 is this data without this $30 million house in it, the sensitivity is around, my average is going to change huge. It's going to change from $30 million down to $300,000. So the average is a very sensitive, non-robust statistic on your data. So in order to protect the fact that this $30 million house is in the data set, I would have to add noise to the query result on the order of $30 million. So no matter what question you asked of this data set, if you asked the average of this data set, I would always be telling you $30 million, even if that house wasn't in there, because there was a potential of a house costing $30 million being in the data set. So what you can do is actually calculate the median, and they do this in housing all the time. It's a better indicator. So if you take any one element out of those 4 houses out of the data set, your median isn't going to change very much. So no matter what house you remove, your median is only going to vary by around $10,000. So to protect the true value of any home in that data, I can perturb a query result just on the order of $10,000. So what that's doing, by doing a smart low sensitivity query, we can preserve privacy but get much more usability out of the data set. So that's really what differential privacy does. It trades usability for privacy. So if you don't get the usability correct, your privacy is going to be maintained, but your data is going to be useless. So the primary technique for implementing differential privacy is to add a random Laplacian noise to the result of your query. And the Laplacian term here, you said is this delta M, the sensitivity of your query divided by epsilon. And you take a random draw, add it as noise before you return results. So that's cool. I can add random noise to kind of hide individuals within the data set and still maintain usability. But a problem here is that if I'm adding random noise all the time, I can just run a query 100 times, right? And then take all those results and beat down the noise and get at the true answer. So keeping track, this epsilon in the differential privacy definition is considered a privacy budget. So that's the term that's kind of affecting how much noise you're adding, but you need to track how many queries have been done against that data set. So it's a key to kind of return the same noise for the same query all the time and not let people collaborate data sets and stuff like that. But still, in practical situations, you can end up adding a lot of noise just based on the query that's being done and trying to do an insensitive query. So there's better techniques. One that we're implementing in Immuta is this sample and aggregate technique, which localizes this sensitivity to your data. Now, what this is doing is you run the same query on each sample of your data, and you aggregate that data in a private way and then add noise. And what that's doing is finding out what the local sensitivity of that query is, and then you can add much less noise and still maintain privacy. But yeah, this is ODSC. We're machine learning people, right? This is what we like. So clearly, when you throw data at this mess of math, it's going to be private because no one understands how this stuff works anyway. We have like some models that approximate, and we have some training techniques that seem to work, and people show cool things, and that's a big mess that I don't know how it works, and it's got to be private. But that's actually just not so. Researchers have attacked public APIs of machine learning models where they've trained these public models. And then what they do is after they train the models, they attack the models with something called this model inversion attack. And there's a link to the paper here. But what they do is they're able to apply noise and kind of go through the model once it's been trained and extract the model parameters out of it. So they did this on image recognition, and they pulled this weird face out. And you've kind of seen the deep learning, like this is kind of what this network thinks a cat kind of looks like. But that looks pretty specific. And lo and behold, it's blurry, but they were able to recreate that image just by attacking a neural network. And lo and behold, the training data contain this guy. And they're pretty similar. So you think releasing a model publicly that's been trained for facial recognition is protecting the privacy of all the images that went in there, but that's just not the case. So how do we fix that? We get into more advanced machine learning. This is very similar to the sample and aggregate technique, where you break up your data and you train multiple models, and then these multiple models become teachers, and they teach yet another model that then you use to help a student model tag data properly. And then finally this model can be released to the public and is differentially private. And here, like kind of as your teachers are voting to teach this aggregate teacher, this is where you're adding random noise that maintains that privacy guarantee. So this is a big paper, and getting into the details of it is difficult, but yeah, we can do more advanced machine learning where we're inserting noise on purpose to protect the privacy of the data and the parameters in the model itself, and still get useful things done. So this researcher actually, in the paper, they showed the standard handwriting database and the Street View house number database that the non-private baseline had this accuracy, and accuracy went down a little bit by adding noise and doing the student-teacher business. But they also, which I guess kind of makes sense, right? Machine learning is not good, and now we're adding noise and it's getting worse. Great. But on this diabetes data set with a random forest algorithm, the non-private model got this 93.8% accuracy, but the privacy model actually got slightly better accuracy with yet a privacy guarantee of differential privacy. So it's not all doom and gloom. I think there's research to be done to figure out the right ways to do the machine learning in a private way, but they've shown that you can definitely do machine learning and maintain privacy. So yeah, in summary, yeah, the laws are catching up to your data, and we got to come up with better data science techniques to preserve privacy and still be able to do what we want in these regulated environments. So hopefully I've opened your eyes to some of these issues. I gave this talk once before, a similar talk, and lots of people came up to me and were like, I thought about nothing of this. So if that's the case, yeah, Amuta can help. We'll be out at the booth. I'm available for questions now or later back there. Thanks for your time.